Alright, this is the second video on distance formula. I really want you to actually go back. If you haven't watched my first video on the concept of distance formula, I want you to go back and watch that right now. This video we're going to go ahead and focus on the actual distance formula and its general use and its advanced uses. And when I say general usage, it's really just finding the distance between a couple points. It's very quick, but there are some advanced uses for it that I would like to take into account here. The prerequisites here are going to be radicals and roots, radical and rational exponent notation, and also the Pythagorean theorem. The theorem we're going to use here is the distance formula, which just says that the distance between the 2 points x1, y1 and x2, y2 on a coordinate plane is given by d equals the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. And as I mentioned in the conceptual lecture, I'd prefer you to never memorize this. Instead, I'd prefer that you actually use the Pythagorean theorem to find the distance between 2 points. But I'm going to go ahead and prove this right now. Suppose you're given a couple points, x1 and x1 comma y1 and x2 comma y2 on a coordinate plane. Now, without loss of generality here, I'm just placing the points in quadrant 1. I could place them anywhere in reality, but I'm just making the proof kind of easier to see by placing them both in quadrant 1. And I want to find the distance between those 2 points. In other words, this distance that's dashed here, I'll call that d. Now, one thing that I want you to take note of, and this is what I gave in the last lecture, is that, or in the conceptual lecture that is that the distance, the horizontal distance between these 2 points, I could call a change in x. That's a change in the x values. That's what this distance, horizontal distance is. The vertical distance between these 2 points, I'll call a change in y, delta y. And a couple things to note here. In this given problem, the change in x is the distance between these 2 points. In other words, it's the larger x value minus the smaller x value. So the distance that x has changed is going to be the larger x value minus the smaller x value. The same thing can be said for the distance that we've changed in the y direction between these 2 points. That is also going to be the change in the y value. The change in y value, basically the upper y value minus the lower y value. So change in y will be the upper y value minus the lower y value. And if you don't believe me, pretend for a moment that y sub 2 is 5 and y sub 1 is 2. The distance here then would be 5 minus 2, or 3. It'd be a distance of 3. That's how you would normally calculate it. So if I'm going to use the Pythagorean theorem, because this happens to be a horizontal line and a vertical line, so they meet at a right angle. So the Pythagorean theorem tells me that d squared should equal to leg squared plus the other leg squared. But we happen to know what delta x is. It's just x2 minus x1. And we know what the change in y is. It's just y2 minus y1. So I'll rewrite this as x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 being squared. That's supposed to be the distance squared. If I take the square root of both sides, I will find that the distance itself is equal to the positive square root of x2 minus x1 being squared plus y2 minus y1 being squared, which is exactly what the distance formula is. A couple things to note. I've had students in the past ask me, does it matter which order I go in for the x values and the y values? Really, it actually doesn't. Because pretend for a moment that this x value here is, I'll use 5 and 2 again. Let's suppose that's x value is 5 and this x value is 2. Well then, obviously the change in x would be 5 minus 2, or 3. And so change in x squared, or in other words, difference between the x values squared, would be 3 squared, or 9. If you would have accidentally swapped the orders and said instead that it was 2 minus 5 instead of 5 minus 2 squared, you would have gotten a negative 3 being squared, which would also turn out to be a 9. So it turns out it doesn't really matter which order that you put the values in, as long as you're using x values, right? One x value minus the other x value within the same parenthesis. And the same thing for the second group, the second term underneath here. You have to have the y value minus the other y value. Okay, so don't mix x and y's together. And I want to remind you that I technically don't bother using the distance formula. I use Pythagorean Theorem. So in this case, find the distance between these 2 points. I might quickly just jot down, not perfectly, but quickly jot down the 2 points. So negative 1 up 1 is right here, and positive 5 down 4 would probably be like over here. So I want to find the distance between those 2 points, negative 1, 1, and 5, negative 4. A couple ways you could approach this. You could either use the distance formula or the Pythagorean theorem, and just note that you want a distance in the vertical direction and a distance in the horizontal direction. So I'll do the Pythagorean theorem approach first because that's the way I tend to want my students to do things. If I'm going to use the Pythagorean theorem approach, I have a right triangle here. This distance for the horizontal leg is going to be, well, I have x equals 5 here and x equals 1 there. So altogether, the distance between these 2 points is 5 minus a negative 1, or in other words, 6. So 5 minus a negative 1, or a 6. That's the distance between the x values. And then the distance between the y values, or in other words, my vertical change. Let's see, this y value is 1. That y value is a negative 4. So the distance would be 1 minus a negative 4. That's how you find the distance between numbers, is subtract one from the other. And this will be 1 plus 4, or in other words, 5. Now, if you do it in the other order, you'll get a negative 5. But the fact is, we're going to be squaring this, so it doesn't really matter. So I have 6 here, 5 there. So therefore, distance should be equal to, or at least distance squared, should be equal to 5 squared plus 6 squared, which is equal to 25 plus 36, which is equal to 5061. So d itself should be equal to square root of 61. Root 61. That's me using the Pythagorean theorem. Had you used the distance formula, you would say, okay, the distance is equal to the square root of x2 minus x1 being squared plus y2 minus y1 being squared. To me, this involves a lot more memorization, which I dislike. Square root of, let's see, I have some junk being squared here plus some other junk being squared here. In this first parenthesis will be x value minus x value, so negative 1 minus 5. Doesn't really matter which order I go in here. And y value minus y value, so 1 minus a negative 4. 1 minus a negative 4. See, this direction looks so computational to me. I don't know. This is going to be the square root of a negative 6 being squared plus 5 being squared. That'll be the square root of 36 plus 25, which is the square root of 61. Same answer. It's just one method looks super computational, and the other one kind of is more conceptual to me. May not be, but it seems more conceptual to me. So that's the typical, very average style of distance, find the distance between 2 points style of problem. Now this problem is from the Yoshiwara textbook, Modeling Graphs and Functions, College Algebra. I think it's the 3rd edition or 2nd edition. They both have, I think, the same problem. Anyway, Leanne is sailing 3 miles west and 5 miles south of a harbor. She heads directly toward an island that is 8 miles west and 7 miles north of the harbor. How far is Leanne from the island? So that's our first part of this question. Now, whenever you do a problem like this, you should really draw a picture because a picture is going to help out. So let's see, she's sailing west and south, and then west and north. So let me go ahead and draw a harbor. I'll call this H. That's the harbor right there. Okay, so there's just some type of peninsula. And from this point on the harbor, she happens to be 3 miles west and 5 miles south. So let me go ahead and go west like 3 steps here. Let's just pretend that's 3 steps right there. So 3 miles. And then she is also 5 miles south. So let me draw that in blue. She's 5 miles south. Let me try to get something that looks a little more like 5. That looks like 5 miles maybe. Okay. So we see that this is where she is when she all of a sudden decides to head directly toward an island that is 8 miles to the west and 7 miles to the north of the harbor. Oops, I drew this harbor in the wrong location. Let me go ahead and move it. I can easily do that. The reason why I know that is because I have to draw north in a moment here. So, all right. So she's heading, this is where she is. She's heading toward an island that is 8 miles west of the harbor and 7 miles north of the harbor. Okay, so she's heading to an island that is 8 miles west. So let me go ahead and draw west for 8 miles. Here's the harbor. Let's go west 8 miles. Well, we already 3 miles of it, so let's go another 5. Let's just say that's about 5 miles. So altogether, let me just put 5 miles here. From here to here is 5 miles. But altogether, that's 8 miles west of the harbor. And then 7 miles north. So let's go and use blue to start from here and go 7 miles north. It should be longer than 5, but shorter than 8. It might be something like this. So this is 7 miles. So let's see if we drawn this correctly. Currently, Leanne is right here. Here is an island. Okay. So let's see, she's 3 miles west and 5 miles south of the harbor. That's exactly where we have her drawn. And she's heading towards this island way up here. And the island itself happens to be 8 miles west of the harbor and 7 miles north of the harbor. So see how this drawing is so important? Because otherwise, this problem would completely have me lost. Now the question is asking, how far is Leanne from the island? So what is the distance? Let me draw it. What is that distance from Leanne to the island itself? One thing to note is that we happen to know what the vertical distance is, and we do happen to know what the horizontal distance is. Now I'm not gonna draw it. Well, yeah, actually I could draw it to scale, but it'll get really messy if I do that. So let me go over on the left-hand side of the page over here and just show you by drawing a right triangle here. So let's just pretend Leanne is right here and the island is right here. We know that the distance vertically is going to be, well, 7 plus an extra 5, or in other words, 12 miles. We know the distance horizontally, or in other words, west, is 5 miles. See, this distance here is 5 miles we denoted, so that'll be 5 miles. That's why this picture is super important, is because all I did, and I'll kind of draw it in here, all I did was complete out this triangle to make a right triangle. Do you see it? Now I'm going to remove it because I don't want it in my way, but that's what we did. So this is the distance between Leanne and the island. We can find that using Pythagorean Theorem. I don't really care about the distance formula. Let's use the Pythagorean Theorem here. Pythagorean Theorem says the hypotenuse squared is equal to the leg squared plus the other leg squared. Or in other words, 25 plus 144 is equal to the hypotenuse squared. Well, 25 plus 144 is actually 169. And I can actually take the square root of 169. That's going to be 13. So she's actually 13 miles from the island at this point. And now, the second part of the question, I'm going to have to actually approach in the next lecture when we talk about the midpoint. So this one I'm going to press hold on and come back to it when I talk about midpoints. But I would like you to really understand this, and then I won't have to redraw anything because I can copy and paste this for my midpoint lecture. But we did part A, and that's a very important part here. So knowing that we're going to come back to that problem in a future lecture when we talk about midpoints, let's go ahead and move on to the last example, more advanced example I have here. Show that the points -2, 1, 0, -1, and square root of 3 minus 1, square root of 3 are vertices of an equilateral triangle. Now I'm going to do this without actually graphing it because, well, I don't know. Graphing -2, 1 is easy. Graphing 0, -1 is easy. But graphing this is a mess. Okay, so I just don't feel like graphing a messy point. But you start asking yourself, how can you show that those points will form an equilateral triangle without even graphing it? How could you show that? Because graphing it might convince you that it's an equilateral triangle, but it's not proving to you that it's an equilateral triangle. So something you should probably note about equilateral triangles, just start thinking about what makes an equilateral triangle an equilateral triangle. Well, one of the most important parts of an equilateral triangle, or one of the most important features, is that all sides have the same length. So if I can show that all the sides have the same length, then it must be an equilateral triangle. How are we going to do this? Well, since these are the vertices, in other words, these are the points that make up the vertex, the vertices of the triangle, we can find the distance between those points. As long as those distances are the same, then we know that this must be equilateral. So what I'm going to do in this case, I'm going to label my points just to make it a little bit easier. So I'll call point 1 -2, 0. Oops, -2, 1 actually. Yeah, some people were like, wait a second. I'll label point 2, 0, -1, and point 3, I'll label root 3 minus 1, root 3. And so let's start finding the distances between these points. Now, notation for distance, there's a lot of different notations for distance. Actually, this is a great time to talk about them. One notation for distance is d of, and then you say like p1, p2. So you're talking about the distance between point 1 and point 2. Or another notation is an absolute value notation with a bar over the points. That means the length of the line segment connecting P1 and P2. These are the same notation. They just mean the distance between these 2 points. Okay? So remember, now I'm going to use the distance formula just because I have too many computations going on. I'm just going to quickly go into the computational mode. I know that the distance formula says take the square root of the difference between the x values squared plus the difference between the y values being squared. So let's see. I'll use P1 as my first. I'll just say -2 minus 0. So those are my difference between the x values. And 1 minus a -1. That's my difference between the y values for those 2 points. That's the square root of, well, -2 squared is going to be 4. And that's 1 plus 1, or 2, being squared is also a 4. That's the square root of 8. And this actually can simplify down as the square root of 4 times the square root of 2, or in other words, 2 root 2. Now let's find out what the distance is between point 1 and point 3. This will be kind of a gnarly computation because it involves point 3. Let's see, so this will be the absolute value of the P1 to P3, which equals square root of, I might need a longer bridge there for the radical, but we'll put that in after we're done here. The difference between the x values. So let's see, point 1 to point 3. First x value is -2 minus the second x value is the square root of 3 minus 1. And notice how I put that in parentheses. I'm subtracting that entire x value. So be very aware of that. To that, I'm going to add the difference between the y values. The y value for point 1 is 1, minus the y value for point 2, or point 3, I'm sorry, is root 3. I'm going to be squaring that. And now I have to clean this up, and this is going to be just wonderful. And I'm being facetious. First of all, that's going to be a negative 2 minus root 3 plus 1, or in other words, a negative 1 minus root 3 being squared, plus 1 minus root 3 being squared. Now I have to distribute out that multiplication in there. And I'm actually going to take this kind of slowly because I think people need to see this multiplication. So I'm going to write this as negative 1 minus the square root of 3 times negative 1 minus the square root of 3. That's what negative 1 minus the square root of 3 squared is. Plus 1 minus the square root of 3 times 1 minus the square root of 3. That's what 1 minus the square root of 3 squared is as well. Well, this is going to get kind of messy, so I'll drop down a line here. Negative 1 times negative 1 is positive 1. Negative 1 times a negative root 3 is a positive root 3. Negative root 3 times a negative 1 is a positive root 3. And finally, negative root 3 times negative root 3 is a positive 3. The next one, plus 1 times 1 is 1, that's easy. 1 times a negative root 3 is a negative root 3. Negative root 3 times 1 is a negative root 3 as well. And finally, negative root 3 times negative root 3 is again a positive 3. So let me connect this up with a radicand here. And now I start canceling like terms. So I have a root 3 right here, positive root 3, and it cancels that negative root 3. I have another positive root 3 that cancels that negative root 3. And now all I have left are 1 plus 3 plus 1 plus 3, which is 8. So that's going to be the square root of 8, or in other words, 2 root 2. So this is a lengthy problem, but I see already, if this were point 1, which it's not, and if this were point 3 and this were point 2, I've already shown that the distance between point 1 and point 2 is 2 root 2, and the distance between point 1 and point 3 is also 2 root 2. All I need now is to show that the distance between point 2 and point 3 is 2 root 2. Oosh. So here we go. The distance between point 2 and point 3 is equal to, well, the absolute value of the line segment, the distance of the line segment between point 2 and point 3. This one won't be as bad because point 2 actually involves an x value of 0, so that'll help out quite a bit actually. I don't mean to write over what I was doing. So let's see. I'm going to actually choose my first x value here to be root 3 minus 1. So let's do first x value, which is root 3 minus 1, minus second x value, which is 0, being squared, plus first y value, which is root 3, minus the second y value, which is a negative 1, being squared. That is equal to, just simplifying it down, kind of, the square root of 3 minus 1 being squared, plus the square root of 3 plus 1 being squared. Now, I could go through a lot of computation here. I could. But I want to show you that this actually we've already done. How do I say this? Maybe I'll just go through and do it. All right. Sometimes you just kind of get exhausted with computation, so I definitely feel the pain that students feel. I'm going to do this very quickly, though. So when I square this out, it's going to be root 3 times root 3, which is 3, minus root 3 minus another root 3 plus 1. And then the second one, when I distribute that out, it'll be 3 plus root 3 plus root 3 plus 1. That's all underneath the radical sign. And then I see some stuff cancels, like a negative root 3 cancels the positive root 3, negative root 3 cancels the positive root 3, and we'll get the square root of 8 again, which is 2 root 2. So I find that this distance here is also a 2 root 2, which means all sides are of the same length, which means it's an equilateral triangle. Very, not, I don't want to say difficult. Conceptually, actually, it's a pretty easy problem because you're just saying, I need to make sure that all sides are the same length. Computationally, it's a little tiresome, but we could do it, right?